Hello, Math 105. All right, so I'm hoping to help you through some of the harder problems in the probability section. So we're going to go over a couple of tough ones. So let's jump down to the quiz. And let's take a look at it. It's question 6 is one of the harder ones here. Let's blow this up so we can all read it. All right. So we have a certain disease that has an incidence rate of 0.8%, a false negative rate of 4%, a false positive 5%. So I want to talk about what the false negative means, what the false positive means, and how to use that with an incidence rate. And I'm going to use a table to do so. In the textbook, this is the section on Bayes' theorem. And Bayes' theorem is one way to analyze conditional probabilities. And so there's a lengthy explanation of how it all works here. Please try to read through that. It is very important. And then there's the formula for Bayes' theorem, which we could just apply. And so here it is in terms of diseases, positives, and negatives. And then there's a walkthrough of one of these problems, very similar to the one we have here with slightly different numbers, and how to go through with imagining 10,000 people. I'm going to take a similar but different approach to it there. All right, so to do so, I'm going to whip out a spreadsheet. And so in the spreadsheet, I need to keep track of some things, like whether someone has the disease or not, and then whether they test. Let's see, we'll go with positive here and negative here. So here are my main cells to work with. Let's highlight those very faint blue. And then out on the edges here, we'll have totals. Diseases and totals, positives and negatives. So let's see. Let's start with the incidence rate. So for the problem we have, the incidence rate is 0.8%. And so what I'm going to do for this is I'm just going to say that there's 100 people total. And so 0.8 of a person has the disease. The textbook solution has you scaling it up, and the video solution in the practice problem has you scale the population up to 10,000 each time, which is totally fine too. But unless you pick a super big number, depending on the percentages, you're going to end up with fractional people somewhere in your table. Okay, so let's see. What do some of these other numbers mean? So for example, a false negative. So a false negative is a conditional probability. On the condition that someone has the disease, the test said they didn't. The test came out negative, but the person has the disease. Right? So in other words, a false negative is, what is the probability someone tests negative knowing that they have the disease? So to reverse that idea in my table, I just need to take 4% of my 0.8 people. So over here, I'm going to say, okay, what is 4%? So 0.04 is 4% times my 0.8 people. Okay, and I get this other fractional number of people. Oops, I put that in the wrong spot, didn't I? Delete false negatives. So they have the disease, but they tested negative. So that's going to be 0.04 times the number of people that have the disease, which is that point. Okay, so there's the number of people that have false negatives according to this. This row has to add up to 0.8. So to get this missing number, I just find out what is the difference between the total and the number of false negatives. Okay, so there's this many people that have the disease and test positive. All right, other area. This column here has to add up to 100. And so this cell right here must be 100 minus 2.8. Okay, so 99.2 people do not have the disease out of 100. So now we're going to use the false positive part. And again, the false positive is also a conditional probability. So in this case, the test came out positive, but that's false, meaning the person didn't have the disease. So that false positive means, what is the probability that someone tested positive when we know they don't have the disease? So conditional probability, and that's the 5%. So what percent of non-diseased people tested positive? So what percent of non-diseased people tested positive? So that goes here. So this is going to be equal to 5%, oops, 5% of the number of non-diseased people. I forgot to type equals. Type equals. Oh, I forgot to type times. There we go. Times the number of people. And that's going to give me the number of false negatives. To get the number of true negatives, this row has to add up to 92.2. So I can just do a subtraction. That is the total of that row minus the number I already know. And so that number goes there. Now I'm almost done with the table. As far as the total number of negatives, that's just going to be the sum of the two numbers above. There we go. And then similarly, there's the sum of the numbers above. So now I got the whole table figured out. So then I can answer any question somebody asks me about this situation. So let's figure out what's the question we're asked. I think we're asked a conditional probability. Compute the probability that a person who tests positive actually has the disease. So I know they tested positive. I want to know what's the chance they had the disease. So again, compute the probability that a person who tests positive actually has the disease. So they're giving me my knowledge up front. The person tests positive. I want to know what the probability they actually have the disease is. So looking at my table, I'm focusing on, I know they tested positive. What is the probability that a person who tests positive? So knowing a person tests positive is the probability they actually have the disease. Okay, so there's my denominator. My numerator is having the disease. So again, I'm finding probability that a person has the disease knowing that they test positive. And the formula for that conditional probability is the probability that they have the disease and they test positive divided by the positive probability that they test positive. So the probability that they have the disease and test positive, that is the intersection of the positive column and the disease row. So again, like I mentioned earlier, this number is my numerator. Divided by probability they tested positive. Well, that's that total under the positives here. So there's my denominator. And so I get a probability of about 13.4%. So let's see what we get. We want to answer this to 3 decimal places. And they want us to compute the probability. Notice they don't state the probability as percent. There is no percent symbol on the outside, so they want a decimal answer to at least 3 decimal places. So 0.134 should suffice. I should be able to come back here and type in 0.134. That's at least 3. I could type more if I want. Let's see if I were going to do one more. 0.1341, rounding up there. Then submit, I should get a happy bean checkbox. Yay! I got it right. Okay, let's do another question. So again, spreadsheets are powerful calculators, and every cell is a little calculator. So this is an expected value problem here. I'm going to do a different expected value problem, but that should help you do this. So here's the problem I'm going to do. So let's see. This was this ease problem. Tab. Here we're going to do expected value. And remember, expected value is just an average. Often, it's referred to as a long-term average. Or a weighted average. Okay, so here's the situation I'm going to imagine. I am going to play a game with a friend where we flip 3 coins. And let's say they're fair coins. Fair coins. No. Okay, so if the coin is fair, that means I'm just as likely to get a head as a tail. So probability of getting a head is 50% or 1/2. Probability of getting a tail is 50% or 1/2. Now I'm flipping 3 of them. So the first flip has 2 possibilities, the second flip has 2 possibilities, and the third flip has 2 possibilities. Whenever you have possibility after another possibility after another, you get to multiply the options. 2 times 2 times 2 is 8. So you can draw this out in a tree if you wish. We're going to have 8 different outcomes. And so you're going to have to take my word for this, draw a tree if you want to verify it. And what I want to do is I want to count the number of heads. So my belief is that I'm either going to have 0 heads, 1 head, 2 heads, or 3 heads. As far as the probability of getting each of these, let's see, probability of getting no heads, well, there's only one way that can happen. I get 3 tails in a row. So there's 1 way out of 8 that can happen. And I claim there's 8 different ways it can happen. As far as getting 1 head, well, that means the head either came up the first time, the second time, or the third time. So that means there are 3 different ways that can happen, 3 out of 8. Now getting 2 heads means I got 1 tail. That tail could have happened on the first try, the second try, or the third try. So again, there's 3 out of 8 ways that could happen. All heads, only one way that can happen, head, head, head. And so that's 1 out of 8. So as far as counting heads, those are my simple, there's 4 simple events. As far as looking at heads or tails, there's 8 simple events. So again, it depends on your perspective. Bottom line is, when you add up what all of your simple events, whatever they are, they better add up to 1, otherwise you miss something. Okay, so there's my 100%. So it adds up. All right, so I did my probability distribution. Now, basically what the probability does is it weights the number of heads that I'm going to get. So I'm likely to get 2 or 1 or 2 heads. I'm less likely to get 0 or 3 heads. And so to find the average here, what I need to do is just multiply the probability times the number outcome, 0, 1, or 2. So there's 2 ways to do this. So one way is to make another column where I take my possible x values, that's the number of heads, and I multiply by each of their probabilities. So to do that, I just go equals, take my x value, and then multiply by its probability. And then I fill that down. So now I've weighted each of my heads according to their probability. And so then if I add them up, that's my weighted average. So what this says is, on average, I should expect to get 1.5 heads. Well, that kind of makes sense looking at the table, right? Because I'm just as likely to get 1 head as 2 heads. What's right in the middle of 1 and 2? Why 1.5 is. Reasonable? other way to think about this is if let's move these suckers over a little bit. If I just think about the frequency, not the relative frequency. Remember, probability is another term for relative frequency. That's the empirical or the experimental definition of probability. Frequency here would just be 1, 3, 3, 1. And those are the weights of each of these guys. So if I want to calculate the average, my numerator would be I have a 0 that happened once, and I have a 1 that can happen 3 different ways, and I have a 2 that can happen 3 different ways, and I have a 3, and I have a 3 that can happen 1 different way. And I divide that by the total number of things that can happen, 8. There's my 1.5. Now, what I have here is the sum of a bunch of products. And it turns out the computer has a formula called the sum product. And what the sum product command says, well, give me your first list of numbers, then put a comma and give me your second list of numbers, and then close the parentheses. And it will multiply them row-wise and then add them up. Whoa, oops, I want to do the probabilities. Sorry, wrong column. Again, some product command needs the relative frequencies, not the frequencies. Highlight those guys, comma, highlight these guys, close parentheses, and there's my 1.5. So there's multiple ways to make a spreadsheet do this or to do it by hand. Bottom line is 5 is the average value here of my random variable, which is the number of heads. So average value of heads is. In other words, if I played this game over and over and over like a million times, and I added up all the heads I got and divided by a million, I should get about 1.5 heads per try. The middle value. Okay, so now I'm going to change the game a little bit. So let's get a new tab. So again, here's the game. We're going to make it a little more complicated. We're going to flip 3 coins. And you have to pay $1. Right. And then what's going to happen is you will profit $1 per tail that you get. What I want to do is I want to look at the possible profits for the number of heads I can get. Spell that right. No, all right. So if I get no heads, I actually lose $1. I got no heads. Right? I have to pay $1 flat. All right. If I get 1 head, then I should profit $1. So I pay the guy $1. I get a head. He's going to pay me back 2, so that my profit is $1. What I walk away with after I paid my money. If I get 2 heads, my claim is the profit is 2. And if I get 3 heads, the profit is 3. And the question is this going to be a fair game for me to play? So to figure that out, I'm going to find the long-term average of playing this game. Oops. So the probabilities for each of these events. The probability is like we had before. It's going to be 1/8. 3/8. And again, since we're doing the calculation, we have to type equals first. 3/8. Okay, equals 3/8. The harder part of these problems is coming up with each of these probabilities. And I just made a mistake in that. How much probability is there's one way that can happen. So 1/8. So then what I just need to tell the computer is to give me the sum product of these guys here, the weighted average. And that's what's called an expected value. Expected value is a long-term average. All right, so to do so, I just say, hey, computer, what is the sum of the products of these two columns, profit versus their chance? It says 1.37. Hey, it's a fair game. Actually, it's not really a fair game because I'm going to make out, and whoever's I'm betting against is going to lose money. Let's double check I calculated that right. Take my profit, -1, 1, 2, and 3, and multiply by the associated probabilities. That is correct. Yeah. So it turns out this is not a game that would be profitable for a casino because they would lose money. Because on average, if I played this game 1,000 times, I should expect to win $1.38 per try. So after 1,000 trials, my average winnings are 1.375 per trial. So my total winnings should be equal to total number of trials times the average value per trial. And so I would end up winning $1,375. Now that's profit, right? That's my profit. That takes into consideration that I paid $1 to play. Pretty cool, huh? So this is not a game you're likely to find in the casino because it pays off too much. So the casino might say, well, we apparently need to charge more for this game if we're going to let you profit in these ways. And so the casino might say, hey, let's charge $2 to play and see if that gets more fair. Still not fair for the casino because you're still winning $1.25. So spreadsheets are fun because they allow us to experiment. What if the casino says, maybe you need to pay $3? Whoa, that's not working out so good. Profits must be too high here. Maybe we should pay $10 to play this game. You would still come out 25 cents ahead on average in playing this game, even if you had to pay $10 up front. Interesting. A lot of fun things we can do with probability. Again, expected value is a long-term average. So those are the harder problems in this type of situation. We have expected value. We have to evaluate what's the value of each opportunity and what's the probability of each opportunity. And then we multiply those guys together, and then we add up the results. On a spreadsheet, some product does that for us. Alternatively, we could make an extra column of those products and then add them up. Other thing, if you're working with conditional probabilities where you have multiple options to work with, a contingency table like this is a nice tool to work with. And a spreadsheet helps with those calculations, working on different conditions and situations. All right, that's it for now. Have fun, do good math, stay in touch. Bye-bye.